attending our demonstration. My name is Chad Lamb, and I'm the Chief Systems Architect here at XKL. We'll be presenting to you a demonstration of the capabilities of a unique optical transport solution, the XKL eVelocity platform. This is the first of its kind optical transport platform, combining DWDM and a flexible statistical multiplexing technology. The XKL eVelocity platform integrates the ability to statistically multiplex customer traffic and the optical aggregation capabilities of dense wave division multiplexing, or DWDM. This demonstration will focus on the statistical multiplexing feature only. First, we'll describe what is statistical multiplexing. Next, we'll describe line utilization and how it plays a role in this demonstration. And then we'll get right to the demonstration of this technology by showing you a live demonstration. What is statistical multiplexing? This graphic depicts two aggregation techniques, TDM, or time division multiplexing, and statistical multiplexing using deficit-weighted round robin. In the simplistic TDM approach, each client port is assigned a time slice on the line side. And you can see here in this graphic that all 10 clients are being aggregated onto the single 100 gig line. The colors represent actual packets being offered, whereas the white represents idles or idle characters. As the client traffic is aggregated, the TDM processing is going to assign that client to a time slice regardless if he's offering a packet or an idle character. In doing so, you can see here how inefficient the line side utilization is. In the eVelocity 100G platform, where we're using statistical multiplexing, we are able to aggregate many more clients than the TDM approach. What we're doing here is intelligently aggregating the client traffic. If a client is not offering a packet, the eVelocity platform will move on to the next client. In doing so, we're stripping off all of the idle characters and packing the 100G line side much more efficiently, effectively filling the pipe. Line utilization refers to the percentage of the line rate that is occupied with Ethernet packets. Typical line utilizations in a network range from anywhere between 15% and 50%. What this means is that between 50% and 85% of the time, your router port is not passing any packets. It's idle. If you looked at any typical network where the router port is occupied at 50%, once it gets to that level, the system administrator starts thinking about adding another router port. What this translates to is a lot of inefficiencies on the line side, and that's where the eVelocity platform comes in, to try to maximize your investment in the DWDM optics. Here is the demonstration setup. We have 4 test sources. We have copies that are made of those test sources so that we can create up to 24 10 gig E streams. We will demonstrate that aggregating all 24 of these 10 gig streams down a single 100 gig line is possible. This is done in an optical transport platform, not in a layer 2 or layer 3 switch. That's very unique in the industry. While each of the test sources are running at a 10 gig E line rate, the line utilization of each port is at 60, 50, 40, and 30%, as shown here. We're using standard variable interpacket gaps and random frame sizes from 64 to 1518 bytes. All of the packet streams are going through the source replicator, which is making identical copies of the input packet stream and feeding those copies to the eVelocity platform, the unit under test. We have the initial condition for the demonstration already connected, which is the first 4 10 gig E test sources are fibered to the eVelocity platform, as you can see here. Now looking at this graphic, you're showing the initial test setup. 4 10 gig E streams for a total of 40 gig of client-side services. Note that the total packet data offered is only 18 gig. This is because we're using line utilizations of 60%, 50, 40, and 30. Adding that up summarizes to 18 gig of total payload. Next, we'll access the system and show a few counters for the interfaces. You can see here that only 10 gig E streams are coming in on the first 4 clients. These are the only active ones at the moment. We're showing you the number of transmit and receive packets, and we're also showing you the line-side 100 gig ports and the counters. Since we were providing a total of 18 gig of packet data on the client side, the line-side 100 gig port has plenty of available bandwidth to service more clients. So we'll add more client bandwidth now. This graphic is showing our next setup. We've added more client services. We have 12 10 gig E streams for a total of 120 gig of client-side services. Note that the total packet data being offered is 54 gig. Accessing the system, we can see here that only 12 clients are active at the moment, showing the total number of transmit and receive packets. Since we were providing a total of 54 gig of packet data on the 12 10 gig E clients, the line-side 100 gig port still has plenty of available bandwidth to service more clients. This is a similar setup to a 10 by 10 gig muxponder solution using a TDM scheme. However, we're using statistical multiplexing and we have 12 10 gig clients. Other than that, it's very similar and comparable. However, you can see here that we're only 54% utilized on the line side. So we'll add more client bandwidth now. This graphic shows our next setup. We've added more client services. We have a total of 20 10 gig E streams for a total of 200 gig of client-side services. And note that the total packet data being offered here is only 90 gig. So our line-side 100 gig port is only 90% utilized. Accessing the system, you can see the statistics from these 20 clients. Since we're providing a total of 90 gig of packet data on the 20 gig, 10 gig E clients, the line-side 100 gig port still has available bandwidth to service even more clients. We're at 90% line utilization on the 100 gig port, but we're servicing 200 gig of client-side services. In a typical TDM approach, this would require a second DWDM wave to be installed in your system. So we have saved one wave in the process here of doing statistical multiplexing instead of the traditional TDM approach. Now we're going to add more client bandwidth and really stress the system. This graphic shows our next setup. 24 10 gig E streams for a total of 240 gig of client-side services. Note that the total packet data being offered here is 108 gig. So obviously 108 gig of client-side services will not fit down a 100 gig pipe, so we expect to see some client traffic being dropped at this point. Let me show you the statistics again by accessing the system. You can see in the statistics here that the velocity 100G line-side port is dropping packets. We saturated the port in order to demonstrate another capability of the system. Each client port has a soft configurable classification assigned to it. By default, all clients are set to the same classification. This classification can be thought of as a priority level. The weights of the deficit-weighted round-robin algorithm are controlled by this setting. Increasing the priority level on a particular port will allocate more bandwidth to it. This is oftentimes referred to as bandwidth shaping. By soft configuring client classifications, you can control the allocation of bandwidth to that client. Next, we will adjust the classification of the first 2 clients. In the current state of the system, all 24 virtual interfaces, or VIFs, are assigned the same class, which is class 3. We will increase the priority of VIF 0 and 1 by decreasing the class number to 2, but just for these 2 interfaces to demonstrate this capability. So we've assigned a class 2 to virtual interface 0. In doing so, we've upped its priority, and you can see here that Virtual Interface 0 is no longer dropping packets. However, there is still 108 gig of total client bandwidth. Since VIF 0 is no longer dropping any packets, the other lower priority clients are dropping more packets. Similarly, we'll adjust the classification for VIF 1. And you can see here the same effect. VIF 1 is no longer dropping any packets, and yet you can see slightly increased packet drops on the other lower priority clients. So in summary, we provided a brief demonstration of the statistical multiplexing feature of the XKL eVelocity platform. We showed the benefits of this over a simple TDM approach. We demonstrated the approach can provide 200 gig of client services using a single 100 gig line-side port without any packet drops, thus greatly increasing the line-side efficiency of Ethernet transport, effectively doubling it. And finally, we showed you the soft configurable classification assignments, allowing you to shape your bandwidth by prioritizing customer service. We thank you for your time and watching this demonstration.